So it does not depend on t, but it can depend on the time lag. So in that case, if the process is stationary, then I use this expression, okay, because we only have a dependency on the time lag, but not on the time itself. Okay? So the time distance between two sampling points. You understand this? Okay? Now, and there is another thing which we're supposed to consider here. So if the process is stationary, then the autocovariance, okay, at point h is the same thing as the autocovariance at point negative h. So in this case, this is something that also we need to look at. Okay? Do you understand? So there is just an dependency on h, but not a dependency on anything else. Okay, so basically the autocovariance or the autocorrelation both are a function of the time lag and just the time lag, nothing else. Okay? Now, if we go further and we're going to look at basically further properties of a stationary process, okay, so if let's say if y is stationary, then we have that the autocorrelation of the process at point h, so for the time lag h, okay, is basically the same as the autocorrelation of the process at point time negative h. Okay, so when we look at stationary processes, we only just use, okay, for h being greater than 0 here without loss of generality, right? Okay? So this is going to be the same thing, okay? So the autocorrelation, let's say, of today and the next 2 days is going to be the same thing, or was the same thing as the autocorrelation of today and 2 days ago, all right? So time, this is just depending on the time distance, and this is quite obvious why this is, okay? Now, why is that, basically? I mean, this is basically, I mean, this is part of the exercise, but I can consider that here too. So basically, this is because, okay, so here, the autocorrelation at point h is going to be, of course, the covariance, okay, so the covariance of yt and yt plus h divided by the standard deviations, okay, so the standard deviation of yt, all right, times the standard deviation of yt plus h, obviously. All right? And since, of course, I mean, this is that you need to be considering is that the covariance of two random variables does not change if you just change the order, right? So if you change the order of the random variables, then it does not change, right? So here you have the covariance of that two is going to be the same thing as if you change the order. So you have the covariance of y at point t plus h, right? And y at point t, okay? Divided by the variance, okay? So I'm going to shift that 2 here. So this is going to be the variance of yt plus h. So I'm going to turn that around here as well. Okay, so here you have the variance of yt plus h, right? Okay, and square root of that, and of course the standard deviation, which is the square root of the variance of the other one. Okay, so here you have the variance, or let's say the square root of the variance of the other two. Okay, so what I was doing is just I was changing the order. Okay, so here you have that one, and the second one you're going to have that one because the function is symmetric, right? In that sense. So the correlation of A and B is the same thing as the correlation of B and A, obviously. Okay? Now why I'm doing this, and now now there comes the stationarity. So since that does not depend on time, okay, so t, let's say we redefine t as follows. Okay, so it doesn't depend on time, we can do the following thing. Okay, so basically what we have here is that here the covariance, okay, so of yt plus h, and I'm going to subtract here h from this. Okay, so this is going to be something that you see here, okay, and this is equal to also on the other hand as well. So here you have yt and minus h, okay. Again, why is that? Because the autocorrelation or the autocovariance does not depend on time. It only depends on the time lag between the two, and the time lag between the two is now still the same. You see? So that's that didn't change here at all, all right? And I'm going to do this here for the standard deviations too. So here you have the standard deviation, okay, of the first one, okay, so yt plus h minus h here for the process, right? Okay, and times the standard deviation of the other. Okay, so here you have the variance of yt, and here you have minus h here. Again, why is that? Because the variance does not depend on time either, because the process is stationary, right? So since the process is stationary, the variance does not depend on time either. It doesn't even depend on the time lag. Okay, so there is, for the variance, there is the time lag is not important because these two would be equal. All right. Now, why I'm using this? I mean, this is obvious because here you would have that this is going to be the covariance of yt and yt minus h. All right. Here in the numerator, and in the denominator you would have the standard deviation of yt and times the standard deviation of yt minus h. All right. So basically, this is what you see as the final result. Again, but this is just true if the process is stationary. So if the process is not stationary, of course, it's not true, right? But if the process is stationary, then you can see that basically, okay, so the covariance of yt and yt plus h is going to be the same thing as the covariance of yt and yt minus h. So basically, you have here that this is going to be the autocorrelation of the process y for the time lag negative h, so that is going to be equal as well. So here it's not important basically if you consider the past or the future of the process regarding the autocorrelation, because it's going to be the same. Okay, so it doesn't matter. Okay, so let's say the autocorrelation at point 10 and 12 is going to be the same thing as the autocorrelation at point 10 and 8. Okay, so at time t is equal to 10 versus t is equal to 12, or the first example, t is equal to 10 and t is equal to 8 as the second example. You understand? Okay, that's basically it, but this is just for what you have for the stationary process. All right? Okay, is this clear, guys? Now, there is even a weaker sense here for stationarity, namely the so-called asymptotic stationarity. Okay, so this is what I'm also going to look at. So if, let's say, the process is not stationary, but it's, let's say, in the long run, okay, so that means that stationarity in the long run, so let me just define it here formally. Okay, so a y is called asymptotically stationary. Okay, and here, of course, in a weak sense too, if let's say y, okay, if y is stationary in the long run, okay. Now, what do I mean by this? And I'm going to explain this here. Okay, so first off, for the stationary processes, we had the time independency of the mean. Remember that? Time independency of the mean, right? So the mean has to be finite, okay? Leave a little space here. So the mean had to be finite, okay? Right? And the mean, okay, so leave a little space here too, okay? So the mean, all right, here, leave a little space, does not depend on time, okay? Okay. Now, if I say stationarity in the long run, okay, so if I say stationarity in the long run, then I mean that the limit of this expression as t converges to infinity is finite. So the limit is finite, okay, not necessarily the expectation itself, but the limit of the expectation is finite. So the expectation is finite in the long run. So maybe like, you know, the process goes like a little crazy at the beginning, but on the long run it's like, you know, it calms down a little bit. All right? So if that's the case, then maybe you understand what you know what this is supposed to mean. Okay? So maybe you have a little time dependency of the mean. Okay, but the time dependency just disappears. Okay? And of course, the same thing holds for the mean instead. So it's not the mean that does not depend on t, it's the limit of the mean. Okay, so the limit as t approaches infinity, okay, does not depend on t. Okay? Alright, you understand? So how would you identify such a process? I mean, suppose for the stationary process we had a constant mean, right? So this was basically a stationary process where the mean was constant. Okay? Right? You understand? And here, for instance, it could be something like this. Okay, so let's say the mean is something like this. Okay? So the time dependency, right? So the time dependency could disappear in the long run. You understand? Now, this is basically what you have here. And then, in that case, if let's say that is also true for the variance as well, right? Then you basically have that the process is stationary in the long run. Okay? So, or let's say you can say asymptotically stationary. Okay? You understand? Okay, so this is what it means. Okay, I just leave this out. Okay, and the same thing holds for the variance too. Okay, so it's not the variance that's supposed to be finite here, guys. Okay. Okay, and it's not just the variance that does not depend on t. Okay, but rather the limit of the variance. Okay, so this is what it means if you talk about stationarity in the long run. Okay, so the limit again. So the limit of that expression as the time approaches infinity is finite, and the limit, okay, of the variance, okay, so I have this here, so the limit of the variance as t approaches infinity does not depend on time. So it could be, for instance, that the variance, okay, is time dependent at the beginning, okay, but this time dependency disappears. Okay, so maybe to illustrate that, okay, so for, let's say, a stationary process, we had, you know, that the variance is basically time independent, okay, so we always had like just a variation here within, okay, but for, let's say, a process which is asymptotically stationary, you could have, for instance, that the variance is something like this, okay, so maybe something like this. Okay, so here at the beginning, let's say, the process is, okay, I mean the variance depends on time, right? But this time dependency disappears in the long run. Okay, so that might be an example related to that. Okay, so for this condition. All right. So and of course you have that also the asymptotically time independence of the covariance too. Okay. All right. So basically, you have that the limit, okay, as t approaches infinity, of the autocovariance of the process, okay, first is finite, okay, and second, the limit, okay, of the autocovariance as t approaches infinity, okay, does not depend on t, but it can depend on the time lag again. Okay, so it does not depend, bless you, does not depend on t, okay, but it can depend on the time lag. All right. Okay, now this is what asymptotic stationarity is. Okay, so this is asymptotic stationarity. Okay, so we basically mean that you have stationarity in the long run, meaning that, okay, So both the mean and the variance and the mean and the variance do not depend on t, and the limit of that does not depend on t, and of course the limit is finite. And the same holds for the covariance as well. Okay? Now, I'll just give you an example. Now, of course, if you have that, if the process is stationary, then it's called stationary in the long run, right? So basically, if the process is stationary, then it's also asymptotically stationary, but usually not the other way around. Okay, so this is also a remark here, right? Okay, so if, let's say, y is stationary, then y is also asymptotically stationary. Okay. All right. So if it's stationary, then it's of course stationary in the long run. Period. Right? Obviously. Right. So that doesn't change. Okay. Right. So far so good. Okay, so you know what a stationary process is. Okay, so you have the time independency of the mean, the time independency of the variance, and the time independency of the covariance, where basically the covariance or the autocovariance can depend on the time lag. Okay, so that is possible, but not on the time itself. Okay, so not on the sampling point, right? Okay. And you have these kind of asymptotic things. So if let's say, this is something that you also had, if the process is stationary, then the autocorrelation only depends on the time lag. Okay, right? And basically the autocorrelation at point h, okay, so for time lag h is going to be the same thing as the autocorrelation for the time lag negative h. And you have that property also asymptotically hold. So if that property that I was mentioning here just holds asymptotically, then you have stationarity in the long run. Okay, so this is actually what this chapter was about. Now the next one is, and this is the final chapter here from this final subject from the section. So here you have the white noise processes. Okay, so what is a white noise? Okay, okay, you just call it white noise, or you can say white noise process, and martingale different series, or martingale different sequences. Okay, so and martingale difference sequences. Now these are a special type of process. Okay. Now a stochastic process, and I'm going to define this. Okay, so this is the definition. Okay, so Y, stochastic process, is called white noise. Okay. Or a white noise process. Okay. If the following conditions are satisfied, and there are 3 of them here as well. So, okay, so all 3 have to be true. Okay, so the first one is that the expectation of the process, okay, and let's say the corresponding random variable, I mean, you can say that the expectation of the process here without loss of generality is always 0. Okay, so basically the expectation is not just, I mean, the process is not just time, the mean is not just time independent, it's also equal to 0. Now the second is that the variance, okay, the variance of that is sigma, let's say sigma squared, okay, so that means that the variance is constant, okay, so basically where you have that sigma is greater than 0, so the variance is constant, okay, and the autocovariance of the process is 0. Alright? So for, of course, for all time lags that are not 0. So if, let's say, the time lag h is 0, then of course you have that the autocovariance is equal to the variance of the process, which is a constant. But all other cases it's going to be 0. So here the process is not what? The process is not serially correlated. Okay, so any process which has a mean zero, a constant variance, and a zero autocovariance is basically called a white noise process. Okay, obviously, and that is true for all t, right? So basically, this is something that you have. Okay, you understand? Okay, so I mean, of course, how does it look like? It's relatively obvious. Okay, so here you have the time. Okay, so here you have the process, and this is something like this. Something like that. Okay, this is a white noise, obviously. Right? Okay, that's how it looks like. Now, of course, you see that there is a time independency regarding the mean, the time independency regarding the variance, and a time independency regarding the covariance as well. So the process is stationary. Okay, so that is obvious. Okay, so the white noise. Okay, so the white noise process is stationary, obviously. Okay, why? Because the mean does not depend on time, the variances do not depend on time, and of course the autocorrelation doesn't depend on time either. Okay, it's basically not serially correlated. Okay, so white noise is stationary, and of course also asymptotic is stationary as well. Okay, so let's say if the white noise is normally distributed. So, okay, so if yt is normally distributed, in addition to that. Okay. Okay. The notation for normal distribution, you've seen this, right? So the normal distribution is denoted as follows. Okay, so here you have the random variable that follows the normal distribution. So you say you have capital N, and of course the mean is 0. And the variance is constant, so this is going to be sigma squared. And now if that's the case, then you have the so-called Gaussian white noise. Okay, so then basically, then Y is a Gaussian white noise. Right? Gaussian. Sorry. Gaussian. Yes, Gauss. Carl Friedrich Gauss. Okay, so that's okay. In reference to Carl Friedrich Gauss mathematician. Okay, you heard that Gauss distribution, which is a normal distribution. Okay, all right. Okay, so that's how it's called then. Okay. And then, of course, I mean, you can see this here that just because the white noise is not serially correlated, so no serial correlation. Okay, so basically what you have here is that no serial correlation, but it can be dependent. Okay, so it can be serially dependent. Okay, so note that the white noise can be also serially dependent. Okay, so just because there is no correlation, it doesn't mean that there is no dependency. Of course, if it's a Gaussian white noise, then if it's not correlated, then it's not dependent either. Okay. Okay, so here in that case, correlation and dependency are equivalent in terms of the Gaussian white noise, but this is not the case in general. Okay, so if the distribution is not normal, then the two are not equivalent. Okay, so note that, I mean, this is something that we need to consider. So note that a white noise can be serially dependent. Okay. Okay. And of course, probably you remember what serial dependency was. Okay, so meaning that the joint distribution, okay, is always equal to the product of the marginal distribution. I mean, whether or not the process is discrete or not. Okay. Okay. So just because it's serially uncorrelated, it can mean that it is dependent. I mean, if it's Gaussian, then it's not the case, right? So for the Gaussian distribution, it's not the case, but in most cases, it is the case in general. Okay, so just because it's not correlated, it can be dependent still. Okay. Now, if that's even independent, so if let's say if the white noise is independent too, okay, So if a white noise is serially independent, okay, so if, let's say, a white noise, and I call this capital Y, is also serially independent, okay, right, then the notation is as follows, okay, so then we write the following, okay, so here you have yt, and yt is a so-called IID random variable, okay, so I just say IID, okay, and meaning that independent and identically distributed, okay, right, okay, so independent and identically distributed. Okay. All right. And of course, if it's Gaussian, then it's also independent. So in the case if it's Gaussian, then you could also write normally and independently distributed, of course. Okay. So there's another distribution, right? Okay. Now, and this is what the white noise is or was, and now I'm going to define the last one, okay, because this is a very important expression here as well. So the stochastic process Y is called the martingale difference sequence, okay, is a martingale difference sequence if the following condition hold. Okay, so there are two conditions that the process has to satisfy. Okay. Okay, so the first condition is that the mean of the absolute value of the process, okay, is finite. Okay. So the mean of the absolute value is finite. We were looking at yesterday, maybe you remember, we were looking at the mean of the absolute value of the normal distributed variable. Okay. Now here, if let's say the mean is okay, so the mean of the absolute value is finite, and basically then this is the first property that should hold here. And what you have here is that, and this is also what we're looking at, the expectation, or let's say the conditional expectation. So what I'm doing here is this. So the expectation of the process, okay, given, okay, yt minus 1, yt minus 2, etc. So this is something that, given its past, okay, so the expectation of the process, given its past, is equal to 0, okay. So this is the conditional expectation, right? So the conditional expectation of the process, given its past, okay? All right, so this is the, let's say, the past of yt, right? Okay, and then we have a conditional expectation. And this means that the expectation, or the conditional expectation of the process, suppose that given the past is already known, all right, is 0, okay? You understand what it means? I mean, just from the notation point of view, okay? So basically the whole set of all the information that is available at point t, all right? So the previous realization, so there is basically, since the process is given here, or the past of the process is given, there is no more randomness here involved, okay? So there is no more randomness regarding the past of the process. So here at the current state, you have already the observations of the past, okay? So suppose that given the past, and the conditional expectation is 0 given its past, okay? So this is what the martingale difference sequence is, okay? Now I'm going to discuss some properties, and next time I will introduce you to that, okay? But this is actually how the definition starts, and We'll do the exercises next time. So in the next lecture, I'm going to discuss properties of the martingale difference sequence. Okay, so that's what we're going to do then. Okay, so what are the basic properties? This is basically captured by the example or exercise 2.3. Okay, so these are going to be the properties, but I'm going to do that next Thursday. Okay, that was it, guys. Okay, so we stop here, and I'll see you Thursday then.